Newton Newton's law of viscosity is tau x z dash is equal to minus mu dash mu1 into del v x with del v z1 divided by del x. This is for fluid 1. Now for fluid 2 we can write tau x z2 is equal to minus mu2, because we have a different viscosity of fluid with the different viscosity. We can write it as del v z2 divided by del x. Now for solving this, we already have an equation for tau xz, that is this equation, these two equations for fluid 1 and fluid 2. Now substituting the value of 1 in here and substituting the value of 2 in here, we get minus mu dash mu1 dvz1 by dx, which is equal to p naught minus pl divided by l into x plus c1, and minus mu2 del vz2 divided by del x is equal to p naught minus pl divided by l into x plus c1. Since we know that the value of c1 and c1 is same, there we took it as c. Now what we are going to do is that we are going to integrate these two equations, integrating the equations. After integrating, we can see, like for integrating the first fluid, we can write it as dvz1 integral minus mu1 into p naught minus pl divided by l into x dx plus c1 into dx integral. Similarly, for the fluid 2, which we can write as minus mu2 into del vz2 is equal to p naught minus pl divided by l x dx integral plus c2 dx integral c1, because both of these are same. Now after integrating, we get vz1 is equal to minus of p naught minus pl divided by 2 mu1 into l into x square minus c1 by mu1 x plus c2 for fluid 1. Similarly, after integrating the for fluid 2, which we get vz2 is equal to minus p naught minus pl divided by 2 mu 2l into x square minus c1 by mu 2 x plus c2 mu. Now we got a velocity profile both for fluid 1 and fluid 2, but since we do not know the value of c1 and c2 for fluid 1 and c2 for fluid 2, we need to calculate these things. But how can we get these things? For these things to calculate, we need boundary conditions. Since we have three different values of constant, we need three boundary conditions in order to solve for these equations. Now we will work on the boundary conditions in order to solve these equations and get the velocity profile for the given thing. Now, thinking about what are the boundary conditions we can apply, we have this figure in here. So, at x equal to 0, we know that we have two different liquids and the velocity of these liquids has to be same at the interface. For example, for the fluid 2, the velocity which is going to be at x equal to 0 has to be same to that of the velocity of fluid 1. So we got our first boundary condition, that is technically the second boundary condition, that is the boundary condition at x equal to 0, which states that vz1 is equal to vz2. Now, working on this particular boundary condition, we know also we have other we need two more boundary conditions. So let's see. When we say that at x equal to minus of b, the velocity of z1 is equal to 0. So yeah, what does this mean? Since we have the fluid 1 at the below part of the slit, we move down, that is minus at minus x equal to minus b, we see that it reaches to the wall of the slit, and we know that at the wall of the slit any velocity of fluid has to be 0, because the wall is not moving and there is no slip condition. Since following the no slip condition, we need to have a velocity of 0 at the wall. So here we have written at x equal to minus b, the velocity of fluid 1 is equal to 0. Similarly, at x equal to plus b, we have a fluid which is the fluid 2, and at x equal to plus b, that is this distance, we need to have the velocity of 2 as equal to 0. It is understood from the previous case itself. Now, moving on, we have three boundary conditions. We can use these three boundary conditions in order to get and solve the three constants which we need to solve. Now, from this is the second boundary condition, this is the boundary condition which is third, and this is the fourth boundary conditions. So actually we needed four boundary conditions in order to solve the problem, and now we have them. So yeah, applying the second boundary condition, we can simply put x equal to 0 in the equation. In this equation, we can simply put the second boundary condition, that is x equal to 0, and from there we can get vz1 equal to vz2. So we can simply say c21 is equal to c22. This means that both of the constant, that is c11 is equal to c22. So actually there was not four constants, but only two constants which we needed to solve, that is C2 and C1, because for both the fluids the constant was same. So yeah, now moving on with the third boundary condition. Applying the third boundary condition, we can at x equal to minus b, we know that vz of 1 equal to 0. Now putting this into the equation of vz1 which we got here, we get 0 equal to minus of p naught minus pl divided by mu 2 mu dash l into b square plus c1 by mu 1 b plus c2 dash c2 1, and putting the fourth boundary condition, that is b, and vz equal to vz2 equal to 0, we get 0 equal to minus of p naught minus pl by 2 mu 2 l into b square minus c1 by mu 2 into b plus c2 2. Now moving on with the question, we know that we have applied both these boundary conditions very well. So yeah, now from these three equations, this is the equation, let us say that we have three equations, that is c21 equal to c22. Now substituting this with c2, we will be having two equations, P naught minus PL divided by 2 mu dash into mu 1L into B square minus plus C1 by mu 1 into B plus C2 is equal to 0, and the another, this is equal, assuming it to be equation 1, and minus of P naught minus PL divided by 2 mu, which is 2 into L into B square minus C1 by mu 2 into B plus C2 into 2, which is equal to 0. It's just C2. So here we have two constants, C1 and C2. Also we have two equations and we have all the terms known. So if we get two equations and two unknown, we can simply solve them in order to get the value of C1 and C2. So by solving this, we can get the velocity profile and get the values of C1 and C2. So let us solve. After solving, we will get the value of C1 as C1 equal to minus of P naught minus PL into B by 2L into mu of 1 minus mu of 2 divided by mu of 1 plus mu of 2, and we can get the value of C2 is as P naught minus PL into B square divided by 2 mu 1 into L into 2 of mu 1 into divided by mu 1 plus mu 2 into is equal, which is C2. Now we can put these values of C1 and C2 and get the value of velocity profile, as well as we can get the value of flux profile after putting the value of C1. After putting these value in velocity profile, we can get the velocity profile itself. So now let us write the final flux profile which we will get after putting all the values of C1. Tau x of z is equal to P naught minus PL into B divided by L into x by B minus half of mu 1 minus mu of 2 divided by mu of 1 plus mu of 2. This is the flux profile which we get for two adjacent fluid flowing through a slit. So actually the flux profile which we got here has an equation this, and to get the velocity profile we need to substitute both of these values to the initial equation which we got. Here we have the equation, and in order to get the velocity profile we need to solve and put the values of C1 and C2. Now, after putting the values of C1 and C2, we will get the velocity profile for each of the liquid fluids 1 and 2. Velocity profile for, let's say, for fluid 1, that is the lighter fluid, that is the heavier fluid, equal to P naught minus PL into B square into 2 mu 1 L into 2 mu 1 mu 1 plus mu 2 plus mu 1 minus mu 2 mu 1 plus mu 2 into x by b minus x by b ka whole square bracket. This is the velocity profile for fluid 1. Which we got is from this equation after we put the values of C1 and C2 and did all the necessary arrangements. Since this C21 is equal to this C222, So we can please put the value of this C2 in here, and the C1 which we got from this, we can simply put this here, and after doing all the necessary calculations we get the values of velocity profile for 1. Now moving on and solving for velocity profile of fluid 2, we get Vz2 as P naught minus PL into B square divided by 2 of mu into 2 L into 2 mu 2 divided by mu 1 plus mu 2 plus mu 1 minus mu 2 divided by mu 1 plus mu 2 into x by b minus x by b ka whole square. From this we got the two velocity profile for each of these, velocity 1 and velocity 2. Now we can say that we can get the values average velocity. To solve for the average velocity, we have a formula which is Vz average is equal to 1 by b, which is the distance, and integrating the velocity of either of the profile. Like if we are talking about the profile 1, we can simply write it as 1, and then we can integrate for only the velocity of the first liquid. So since the velocity of first liquid is in the bottom part of the slit, we can simply write integrate it from minus b to 0, and we can integrate the velocity of the first liquid as this, and for the second liquid we can write it as this, and we can simply again integrate it from 0 to b because we have it in the upper part of the slit. So for the liquid 2 we are going to integrate this way, and yeah, from this we can get the average velocity of both the liquids. Now in order to calculate the average velocity, after calculating the average velocity and integrating these things, we get velocity of liquid fluid 1 average velocity, which is P naught minus PL divided by 12 times mu 1 into L, we have B square here, and 7 into mu 1 plus mu 2 divided by mu 1 plus mu 2. So yeah, we got the velocity of fluid 1, and similarly we can get the velocity of fluid 2 as Vz2 average velocity is equal to 1 by b 0 to, after solving you get P naught minus PL into B square by 12 times mu 2 L, mu 1 plus 7 times mu 2, mu 1 plus mu 2. So here we got the average velocity of the first fluid, average velocity of the second fluid, we got the velocity profile for the first fluid, we got the velocity profile for the second fluid, we got the flux profile for both the fluids. Also we got, for in order to solve these things we needed the values of constant 1 and constant 2. Since after solving the flux profile for both the fluids separately, we got to know from the boundary conditions that we have only two constants for which we needed to solve the problem, and this is how we got the complete flux profile and the velocity profile. Alright, now that we have unpacked the physics and fluid dynamics of two immiscible fluid, one flowing through a slit and interacting with an adjacent fluid, it's time for the most exciting part, real world applications. This is where theory comes to life. Inkjet printing. Let's start with something familiar. Inkjet printers. In these devices, ink, often immiscible with the surrounding air, is precisely ejected through microscopic slits. The interaction between the ink and air is finely controlled and allowing for razor sharp and accurate printing.
Oil recovery techniques in petroleum engineering. Enhanced oil recovery involves injecting water or gas, both immiscible with oil, into underground reservoirs. These fluids move through a narrow slit or porous fractures, pushing trapped oil towards extracting less. It's a powerful real-world demonstration of immiscible fluid interaction in a confined space. Microfluidic and lab-on-a-chip devices are another example of it. Real-world applications in which cutting-edge biomedical tech, immiscible fluids like oil and water flow side by side through microchannels. This enables precise mixing, separation, or diagnostic tests or at all micro scales. The devices are transforming healthcare with rapid and low volume testing. Another example is coating and film deposition in industrial manufacturing, like creating display screens or solar panels. Slot die coating is used to spread a thin liquid film through a narrow slit. When the liquid involves are immiscible, a clean, stable interface is formed, critical for consistent, high-quality coating. Emulsification in food and cosmetics, and finally, in food and cosmetic industry, two immiscible fluid like oil and water are forced through slit or nozzles to create stable emulsions. These are the foundation of product from salad dressing to moisturizers. So as you can see, these are the simple yet elegant concept. Immiscible fluids flowing through and beside slit underpins technologies that range from everyday to extraordinary. And with that, we wrap up this video and hope you find this video interesting, and thank you.